In this video, I'm looking at how we can interpret what a line graph is telling us. We know that when we conduct experiments, we're usually trying to find the relationship between two quantities. Usually that is the aim or the objective of our experiments. That's how scientists have come up with the laws that we know, the equations that we use to express those laws are the experiments in which data was collected and analyzed in order to come to a decision as to how one variable is related to another. And very often in your labs, you vary some quantity, look how some other quantity responds, take some measurements of both quantities, and very often you do a graph to illustrate how one quantity varies as the other varies. And then you are expected to analyze your results. Well, the graph is a part of the analysis. The graph is drawn and interpreted to come to a conclusion about the relationship between the two quantities. So what I want to do is to ensure that we understand how to interpret graphs. So this is general information that you will apply whenever necessary in your analysis of data. Some basic information to begin with. Well, I'm not using the slideshow because I want to be able to jump to specific slides at specific points. So generally, a graph gives you a picture of the relationship between variables, like I said. Our graphs that we draw in physics are always, well, usually line graphs. We don't draw bar graphs and histogram and pie chart. Our graphs are line graphs for the most part. I don't think I've ever seen a bar graph in physics. A line graph can show that there is a correlation between two variables. That simply means that when one variable is changed, it affects the other. There is some relationship between them. If you plot a graph and the points don't fall on a straight line or any line, straight or curved, they're just scattered all over the place, it means that the value of one quantity, when you change that, did not affect the value of the other. It's like the two things have no correlation between them. So what you do to one variable that you normally call the manipulating or independent variable, if it has no effect on the responding variable, then you could say the variable is not responding. It's not dependent on the other. So you would not get a line for your graph. But a line graph would show you that there is a relationship between the two. So every line graph is telling you that there is a relationship between the two quantities that you plot on the x and the y axis. We can go a step further and determine if the graph is telling you that there is a positive correlation between the variables or there is a negative correlation between the variables. Positive correlation just means that as one variable increases, the other variable increases also. So if as one quantity increases, the other increases, we say that there is a positive correlation between them. On the other hand, if when you increase one quantity, the other quantity decreases as a result, we say that there is a negative correlation between them. Now, one of the things I've observed over the years, no matter how often I say it, it's still, by the time students get to interpreting their graphs or the data that they have collected in a table, very often students will say, as x increases, y increases, and therefore they are proportional to each other. That is not necessarily true. If as x increases, y increases, you can conclude that there is a positive correlation between them, but the relationship may not necessarily be a directly proportional one. So directly proportional relationship has to satisfy an extra condition. For your directly proportional relationship, your graph needs to be a straight line that is passing through the origin. So when relationships are directly proportional, it means that not just as one increases, the other increases, but the other must increase by the same factor. So if you double one, the other one is doubled. If you half one, the other one is halved. That would indicate direct proportionality, which is a step beyond just positive correlation. So that's one thing that I want to say, and I'm going to say it a few more times. So generally a line, we know we have drawn lines of best fit. So when you do an experiment and you get data based on measurements that you have taken, several factors will influence how accurate those results are. The skill of the person taking the measurement, the instrument that you're using may have faults or features that introduce a source of error in your measurement. It may just not be accurate enough or precise enough to give you readings that will plot into a perfect line. So from we learn to draw graphs in grade 10, we learn to draw lines of best fit. Meaning you draw a line that fits the trend, the pattern of the points as best as possible, even though all the points may not fall exactly on the line. And we know how to draw a line of best fit, trying to ensure that it fits as many of the points, it passes through as many of the points as possible. And those that don't pass through the line should be, as far as possible, evenly distributed on either side of the line. The line of best fit does not have to be a straight line of best fit. If it's a straight line of best fit, you draw it with a ruler. If it's a curve, you draw it with a flexi curve or freehand. But it doesn't mean that it is not a best fit line. So a best fit line does not have to be straight. That's another point I want to make. A best fit line does not have to be straight. Most of our graphs, we end up drawing straight lines, but it doesn't mean that all graphs have to be straight lines. You just look at the pattern of the point, the scatter of the points and the context, and you very often will be able to determine if the line should be a straight line or if it should be a curve. If the line of best fit is straight, then we can say that the relationship between the two quantities is linear. So linear goes with straight line, okay? If it's a curve, then it is not linear. But linear does not necessarily mean that the two quantities are proportional. So we're moving from, as one increases, the other increases, they are proportional. That is far from the truth. As one increases, the other increases means that there is a positive correlation. It may not necessarily be a linear relationship because one can increase and the other increase and you don't get a straight line. We'll look at some of those examples of graphs. In order for you to say that there is a direct proportional relationship between two variables, it must be a linear graph. So you must have a straight line, and the straight line must have a positive gradient, so it's sloping to the right, and it must pass through the origin. So the criteria for you to say X is proportional to Y is more than just as one increases, the other increases. It must increase proportionally, and that would be illustrated on a graph by a straight line passing through the origin. Now, in relation to passing through the origin, it's not all the time that your graph actually starts from 0, 0. So that may not be evident from the graph, but it simply means that your y-intercept is 0. Whether you can identify that 0, 0 on the graph, or you calculate the y-intercept, if it's directly proportional, then the y-intercept would be 0. If the y-intercept is not 0, it doesn't mean that it's not a linear relationship, because we know the equation of a straight line is y equal mx plus c, where c is the y-intercept, right?
Yes, miss.
if that C is 0, if the y-intercept is 0, then your x and y are directly proportional. So the equation is basically y equal mx because the C is 0. If the C is not 0, you have a linear relationship because yes, you have a straight line graph, but it's not directly proportional. So if you double x, y won't double. If y equal mx plus c and you double x, y will now be equal to 2mx, but still plus c. So you're not going to get a doubling of y if you double x. So I'm saying that a linear relationship is not necessarily a direct proportional relationship. All right. I mentioned the equation of a straight line, which is in the form y equal mx plus c. And we know that m is the gradient and c is the y-intercept. And what we mean by the y-intercept, y is on the y-axis here, on the vertical axis, and x is on the horizontal axis. All it means, the y-intercept means, is the value of y when x is 0. So your y-intercept here is the point where that gives you the y value when x is 0. This is x, and that's y. So when x is 0, assuming that we have 0 at the origin here, y is c, and that's obvious from the equation because if x is 0, then m times 0 is 0 and y is equal to c. We tend to use that intercept more often than we use the x-intercept, but you still need to know what the x-intercept is. It's just the value of x when y is 0. So if these are your y values, so y would be 0 here, where the line cuts the x-axis. So this is your x-intercept. When y is 0, according to this same equation, when y is 0, mx will be negative c, and therefore your x value would be negative c over m. So your x-intercept is negative c over m, your y-intercept is c, and the equation of your straight line, m is your gradient, of course, and your general equation of the straight line, y equal mx plus c. Note that the line here is not passing through the origin, so this is not showing direct proportionality. It's showing a linear relationship, but it is not direct proportionality. If c was 0, then that's when the line would be down here, and you would have your direct proportionality. So have a look at this table, and let's see what we can gather from the data in this table. X is our independent variable. So we have x there increasing from 1 to 8. A, B, C, D, E, and F are representing different values of y, so we will look at them one at a time. Comparing A with x. X increases from 1 to 8 in steps of 1. A is increasing from 4 to 32. So the fact that A increases as x increases, we can say that there is a positive correlation between them. If we look a little more closely, we can also see that A increases by 4 each time x increases by 1. So A is basically 4 times x. So there is a linear relationship between them, and it's a directly proportional relationship. A is equal to 4 times x. So a graph of A against x would be a straight line passing through the origin, and that is our evidence for direct proportionality. If you double x, A is doubled. X increases from 3 to 6, A increases from 12 to 24. Okay? For example, let's compare another set of y values, B with x. As x increases, b increases. So that means there's a positive correlation between them. But if we look at the rate of increase, b is not increasing by the same amount each time. B increases by 3, then by 5, then by 7, then by 9. So there isn't a directly proportional relationship between x and b. You might notice that b is actually x squared. So we could say that b is proportional to x squared because b is actually equal to x squared. B is 1 times x squared. So b is proportional to x squared, but b is not proportional to x. So there is positive correlation between b and x because as x increases, b increases, but the relationship is not linear and it is not directly proportional. The graph of b against x is a curve. The rate of increase, the gradient of the graph, is not constant. For you to have a linear relationship, then you must have a constant gradient. This gradient is not constant. The gradient is increasing as x increases. So while there's positive correlation here, there is not a linear relationship between b and x. If it was a graph of b against x squared, then we would get a straight line passing through the origin. Comparing the c values with x. As x increases, c increases. So we can say there's a positive correlation, but the rate of increase is not constant. C increases by 12, and then by 10, and then by 8, and then by 6. So the rate of increase of C is getting less and less. The rate at which C increases is decreasing. So C increases as X increases. So there's positive correlation, but it is not a steady increase. So there is no linear relationship between C and X. If we look at the graph, C increases as X increases, but the rate of increase, that's the gradient of the graph, is decreasing. So it's not a linear relationship because it's not a constant gradient, but there is positive correlation because as x increases, c increases. So you see, there's only so much that we can get from the values in a table. The graph helps us to get a better picture of what's happening. Because both C and B had a positive correlation, but neither of them was linear, and the curves, for B, the gradient was increasing, for C, the gradient was decreasing. If we look at the D values here, for D, for the most part, we see that as x increases, D decreases. There's a slight increase at the last point there. So for the most part, there seems to be a negative correlation, but you know, sometimes you do an experiment and there's a point that just seems off. So for something like that, you could say, for the most part, there seems to be a negative correlation. However, in general, that's in general. But as you can see, the last point there was a slight increase in D while X was still decreasing. There isn't much more that we can say. There is no linear relationship. There is no proportionality. If we compare E and X, again, we have negative correlation because E is decreasing as X is increasing, but this time it is a steady decrease. E is decreasing by 8 units every time X increases by 1. So the graph of E against X is showing you that there is a linear relationship because it's a straight line. There is negative correlation between E and X. Sometimes people refer to this as inverse proportionality. That's not what this is. There is a linear relationship, there's negative correlation, but we will talk a little later about inverse proportionality. And if we look at f, comparing f and x, f is increasing as x increases. F is increasing by a set amount, so f and x are proportional. F is actually 6 times x. So like A, f is proportional to x. However, the factor, the constant of proportionality is not the same. F is 6 times x, whereas A was 4 times x. If we plot a graph of f against x on the same axis with A against x, then these are what our lines would look like. So both have positive correlation, both are directly proportional to x, but for f, the constant of proportionality is larger. F is 6 times x, A is only 4 times x. F has a larger gradient, shown by the steeper line there. Before we look at what inverse proportionality is, let me just look at what it is not. This graph is showing y proportional to negative x. So as negative x increases, y increases. It's a straight line passing through the origin, but it has a negative gradient. So y is directly proportional here to negative x. This is not inverse proportionality. For inverse proportionality, y is proportional to 1 over x, the inverse of x. So if y is proportional to 1 over x, a graph of y against x would give us a curve like this. However, a graph of y against 1 over x would give a straight line with a positive gradient because y is proportional to 1 over x. I hope that helps to shed some light on what graphs are actually telling us.